So today we are going to start our new topic. So basically we are starting electromagnetic induction after completing magnetic effect of current as well as force on moving charge in magnetic field as well as electric field. So these two are very important topics we have already seen, and all those concepts what we have dealt earlier, we will be using those concepts in this chapter. So this is very big chapter and very important chapter, right? So first topic where we will start is magnetic flux. We already dealt electric flux. So today we will see how to find out magnetic flux. So procedure is more or less same. Let's see. So magnetic flux. Before getting into magnetic flux, let's see what we have seen in electric flux. So if in a space we have electric field lines and let's take some imaginary area having area vector in this direction. So small elemental area I have taken, and these red line they are representing electric field and the angle between them is theta. So if I ask what is the magnetic flux passing through this imaginary area, formula was d phi is equal to E vector dot dA vector, right? E vector dot dA vector was the flux, and if I integrate this one, then I will get the total flux associated. Okay, so this was the formula for electric flux. In magnetic flux, only thing this E will get replaced by magnetic field. So this E we will replace with B. Their flux was representing, or it was proportional to the number of line passing through the imaginary area. Okay. Similarly, in magnetic field, that flux will be representing the number of line passing the given area. So higher the flux, higher would be the number of line crossing the area. Now this flux is a scalar quantity. You can see the dot product between electric field and area. Similarly, magnetic flux will be a scalar quantity. So see, if I assume that there exists magnetic field in a space along x direction, and I take some area ds area which will be having area vector perpendicular to its surface and angle between them is theta, then the magnetic flux is given by phi is given by this expression, phi is equal to b dot dA. So you can see that here E, this E is getting replaced by this B. Okay. Now let's first clear the electric flux. So this is the formula for calculation of magnetic flux, and what are the properties? It is a scalar quantity and its unit in which we measure flux is Weber, and this is, there is one more unit that is called volt second. How volt second is coming, that I will tell later. Okay, but for time being, electric flux unit is Weber. Now let's see one example. Okay, so I'll take one simple example so that you will first understand how to calculate flux. Then in the next class we will be seeing how to use that flux. Okay, so today we will just see how to find out the flux. So I have taken one simple example, you can go through. So a square of side 2 meter lies in the xy plane in region where the magnetic field is given by 2I plus 3j plus 4k, and the magnetic flux question is what is the magnetic flux passing through the given area. So if we can write everything in vector form, B already given in vector form, that means what is left is area. So area I will try to write in vector form. Look at the situation, here we have the loop lying on xy plane. So, this is the loop. Okay, it is lying on xy plane. What is the area vector for this? Area vector for this loop is dimension, that is 2 meter side, this 2 by 2, and direction. Okay, so area will be perpendicular to the area vector will be perpendicular to the surface. Here you are free to take any direction of area vector. You may take outward or inward, okay, because this is a flat surface, any direction you can take. So, if I take outward, then I can write 4 k cap, and if I want to find out how much flux is passing through this one, then phi is equal to b vector dot a vector, and this b vector is 2I plus 3j plus 4k dot 4k cap. So, if I multiply, then I dot k and j dot k will be 0, and we are getting 16 as flux. Obviously, this will be in Weber, right. So, this is the flux. Try writing area in vector form. If you have magnetic and field in vector form, you can easily calculate. Now, let us take another situation. I will give you another situation. So, I will clear all this. I am giving you another situation. Instead of placing our frame on x y plane, if I place the frame this way. So, I change the question. This is x axis, y axis, z axis, and now I am going to place the plane or frame this way. Okay, and say it is making 60 degree from z axis. This is the situation, and now I am asking find the flux passing through this frame. This is 2 by 2 frame. This one is 2 meter and this one is also 2 meter. Okay, and you want to find out flux associated. So, question is small change, find flux. Okay, magnetic field I am giving same. So, same field, but the situation is little different. So, first I will try to write area in vector form. So, if I see from top, this is x axis, this one is z axis, and our frame is making 60 degree with z axis. So, from top when I observe, I will observe this angle 60 degree. What is the direction of area vector for this one? Perpendicular to the plane. So, area vector will be something like this. Okay, if this angle is 60, this will be 60, this will be 30, this will be 60. And the magnitude of this one is 4, 2 cross 2, 4. So, area vector, now I can write 4 cos 60 degree I cap, 4 cos 60 degree I cap, and 4 sin 60 degree j cap, 4 sin 60 degree minus k cap, 4 sin 60 degree k cap. So, this will become 2 I cap minus 2 root 3 k cap. This is area vector. Now, once we have area vector, we can find out flux. Phi is equal to b vector dot a vector. So, b is given 2I plus 3j plus 4k, 2I plus 3j plus 4k, and area is given 2I minus root 3 k cap. Let's do the dot product. So, j is not present, right? So I dot I will give you 4 and k dot k here 4 and this one minus 8 root 3, okay, Weber is the flux. So same as the previous one we had area vector along z direction, but in this situation we had area vector making some angle. So I will write that in vector form and after that I will get the flux associated, right. So I hope this whole thing is clear, how to find out flux. So both the cases I have discussed. In this situation, as you can see, the magnetic field is constant. As magnetic field is constant, I will directly multiply, no need to integrate. But what if this magnetic field is variable? So I am placing loop in a region where the field is variable, okay. Then what to do? Obviously we need to integrate. Let us see one example, then it will be more clear. So 16 will be the answer for the first part. Now look at this one. There is infinite current carrying wire and there exists one loop over here. This wire carries current, say I. So wire carries current in this direction and this current is I. So current carrying infinite wire, and because of this wire we know the magnetic field pattern, right. It will be circle whose center will be on the wire and the plane of those circle will be perpendicular to the wire. Now question is, find the flux passing through ring. Find flux passing through ring. So how much flux will pass through ring, and the center of the ring is at the end of the wire, okay. So you can treat this as semi-infinite wire and the center of this ring is on the wire. How much is the flux passing through this one? So as the magnetic field produced by this semi-infinite wire on this plane will be something like this, right. So if magnetic field in upward direction, then magnetic field lines here will be like this. As you can see, there is no line crossing the area bounded by the ring. That means there is no flux associated, okay. All the lines, if you look at the ring, all the lines will be on the same plane and they are not cutting the area bounded by a ring. As there is no flux, there is no line crossing the area, flux associated I can directly say 0. Or another thing I can do to make it more clear, if I take a small area over here, take a small area, right, imaginary area over the area bounded by ring, then this will have area vector in this direction, okay. D area will be like this, and the magnetic field line, you can see that here magnetic field line will be in inward direction. That means the angle between them is 90 degree. So even if I apply formula, d phi is equal to b vector dot dA vector, this b dA cos 90 will give me 0. So the flux associated with the ring is 0, okay. So I hope it is clear. Now instead of placing ring this way, if wire and I am placing ring this way, if I place a loop parallel to the wire, then how much would be the flux? So let us see next example. So there is infinite straight current carrying wire and there is a loop placed beside the wire, and I am asking how much is the flux passing through this loop. You can go through the question once. So figure shows a long straight wire carries current I and a square conducting wire loop of length of side L at a distance A from the current wire. Both the current wire and the loop are in the plane of paper, find the flux of magnetic field of the current wire passing through the loop. So, we need to find out flux, but situation, as you can see, that every imaginary area over the loop will be at different distance. So, the field that will be coming here will be varying with distance, and to get flux now you need to integrate. So, loop is placed at distance a. So, this distance is given to you as a. Let this length is L and this length is L. How would be the field pattern if this is carrying current and taking current from minus infinity and bringing it to plus infinity? Then the magnetic field pattern will be like this, same as the previous one. And the formula for magnetic field by straight wire is mu naught upon 4 pi 2I by small r. This way I can write. So, you can see that magnetic field is a function of distance. So, we can take a small element this way at distance r from the wire of thickness dr. Right, and I'll calculate the flux associated with this one first. So, flux associated with this one will be B vector dot dA vector, which I can write B vector magnitude dA vector magnitude cos 0. Here area vector and the magnetic field both are in same direction. Okay. So, B is from the expression we have mu naught upon 4 pi 2I divided by r. Now, let us write area. What is the area of the strip? So, this length is L and this is dA. So, this will be L dr cos 0 1, okay, d phi. So, this if I integrate I will get flux. So, mu naught upon 4 pi 2I L, these all are constant. I can take these constant out and in bracket I am getting dr by r. Limit r varies from, for this whole area, r is a to a plus L. So, this will be a to a plus L, and we have mu naught upon 4 pi 2 Li ln a plus L divided by right. So, this is the flux associated with this area. As magnetic field was different at different point, we integrated the magnetic field and we got the flux. I hope procedure is clear. What to do when we have a constant field over the area, we can directly write B dot A, but if field is variable, then we will integrate and then we will calculate. Okay. Now, let us move to next one. So, we have now a cylindrical wire and we know how to find out the field inside as well as outside. If I take loop this way, previous case I have taken the loop outside, okay, loop was outside the wire. Now, I am taking the loop inside thick wire, and if the radius of loop is r, this length will be r and let this length be L. And question is, what is the flux passing through the loop? Find flux passing through loop. So again I need to first find out the field inside. Okay, so field lines will be circular again, and if you know the result, then directly you can use the result here. If you don't know, first try finding field inside. So to get the field inside, let wire carries current I, which is uniformly distributed. So current is uniformly distributed over area, and we are interested in finding field at some distance r. So from here at distance r, I will consider Amperian loop. Okay, so get the current which is passing through this area to apply Ampere's law. So current density here J is equal to I divided by pi r square. How much is the current passing through this area only? I inside. So I passing through this area is current density into area pi small r square. Once we have this current, we can find out the magnetic field here. So magnetic field B dot dl, close, Ampere's law I am using, mu naught I in. So mu naught I in is I divided by pi r square into pi small r square. Here I will take B out, and then this is 2 pi r. Okay, if we simplify, then we are getting B is equal to mu naught, this pi will get cancelled out, 2 pi, this 2 pi, and then we have I r square divided by this r and r will get cancelled out. So instead of square, you are going to get only r divided by r square. So this is the magnetic field we are getting, and using this magnetic field I can calculate flux. Okay, so let's calculate it separately. So B we have. Now I'll erase all. Magnetic field at distance r I have. So from here at distance r, to get flux, first I will calculate the flux passing through this part. Okay, so magnetic field line here into the plane, field line direction. If current is this way, then field line here will be this way. So on the element, it will be into the plane. Okay. Let's write flux. Flux is equal to magnetic field d phi is equal to B dot dA. So I can write d phi is equal to B mu naught upon 2 pi I r divided by r square. If you know the result, you can directly use the result. If you don't know the result, because of symmetry, we can find out easily with the help of Ampere's law. So mu naught upon mu naught divided by 2 pi I small r divided by r square into area. Area is, this thickness is dr, right, and this is L. So L dr. Limit 0 to capital R. So here I will put limit 0 to capital R. Then we have mu naught upon 4 pi I divided by r square into L, look at this one, r to the power 1 integration r square by 2. So, upper limit minus lower limit, you will get r square by 2. So, this r square getting cancelled out, and we are getting mu naught upon 4 pi, and in fact this will become 8 I L. Okay. So, this will give you flux passing through this area. So, I hope this example is clear, very simple example. Now, if I make a small change in this one, instead of this current density being constant, if I make current density variable, okay. So, now our current density is variable. So, first part over, current density was constant, current was uniformly distributed. Second case I am telling, now second part, that our current density varies with distance, okay. So, now current density is variable. So, I will change the current density, see the procedure. So, current density is now variable. So, now current density is say J naught R. If current density is J naught R, that means current density is increasing with the distance. So, as you go away, current density is not uniform. So, R is equal to 0, current will be 0, and then as you go away from the axis, then current increases. So, this is the way we have current distribution. First thing I need to find out is how much is the current. So, I will erase this part, and first I will try to find out the magnetic field inside, and for magnetic field inside I need to again apply Ampere's law, right. But the problem here is current density is variable. So, at distance r, if I take loop like this, I need to find out how much is current passing through this area. Okay. So, only this much current you can see is passing through the area. Out of the total current, only some part of the current will be flowing through it. So, if I take small cross sectional area here, how much is the current, this dI in, current through this. So, current density into area J naught into J naught R into 2 pi r dr will be area, 2 pi r dr. Okay. So, this will be the current passing through small area you have taken, and this we need to integrate from 0 to small r. So, 0 to small r if I integrate, then I can see here separately I will write. So, this value will be J naught 2 pi r square integration r cube by 3, small r cube by 3. This is I in, and that I in I will use in Biot-Savart's law to get the magnetic field. So, let us substitute this I in here. So, when I write this I in here, this is J naught into 2 pi r cube divided by 3, that means B will be equal to 2 pi getting cancelled out, and we are getting mu naught J naught r square by 3, right. So, instead of field being proportional to r, like what we got in previous situation, here we are getting it is proportional to r square. Okay. If it is proportional to r square, here the expression will be different now. Now see, mu naught J naught R square by 3 is field, mu naught J naught R square by 3. If I integrate, then I will get R cube by 3. Okay, so one more 3 will come. So here it will become 9, integration 0 to R. So total flux is mu naught J naught R cube L. So this is the expression if we have non-uniform current distribution. Okay, I hope now procedure is clear. We have done the sufficient problem on variable magnetic field. So this whole concept is clear. Let's see some other example. See, so there are two wires or two circular ring. One is having radius R, capital R. This is having radius capital R, and this one is having radius say A, where A is very small as compared to R. So this ring is having very small radius as compared to that bigger one. Now if I ask if this bigger one carries current I, how much is the flux associated with the ring of radius R? So question is find flux passing through ring of radius A. Okay, how much is the flux passing through this one? So for that, if we know the magnetic field pattern, we can easily decide. So first important thing is the magnetic field pattern, and that we have done in the last class, in the previous chapter, right? So if I take current carrying wire, current carrying loop this way, then the magnetic field lines will be like this. So this will be the magnetic field pattern, okay, and as you can see, if a loop is placed this way, a small loop is placed this way, this will have area vector in this direction, while the magnetic field over the surface is making 90 degree. So this angle is 90 degree, and if I apply flux formula, phi is equal to B vector dot A vector, this B vector A vector cos 90 will give you 0. So there is no flux associated because no line will cross this area. In this case, the loop is placed this way. So the pattern what we are getting because of the ring of radius capital R, and okay, direction is correct. So there is no flux associated with this area. So if these two are kept mutually perpendicular, their planes are mutually perpendicular, then there is no flux passing through this ring. Okay, and if I draw three-dimensional diagram with a plane, then it will be more clear for you to understand. So this is on, if this is x axis, this one is y axis, and this outward is z axis. So this is on yz plane, on yz plane. Similarly, this ring is on xz plane. Okay, so this ring is on xz plane. These two are mutually perpendicular. So no flux is associated with the ring. Now if I rotate ring till the plane of this bigger ring and the plane of this ring will lie on same plane this way. So previous case perpendicular planes, and in this case they have got the same plane. So plane of this and plane of this one both are matching. Okay, and question is same. So this has got radius r, this smaller one is having radius a. Right. Now how much is the flux associated? So because of this ring, current carrying ring, field pattern to just now we have drawn. Let's draw it once again. So this is the way there will be magnetic field lines. Okay, due to this current carrying loop, these all will be circular. Okay, so I am not joining these lines, I am just drawing a part of whole line. And if small a is very small as compared to r, then the size of this ring will be very small. If the size of the ring is very small, then I can assume that the magnetic field due to this bigger ring at every point on the surface of this small ring will be almost same as the magnetic field produced by bigger ring at the center. So magnetic field produced by this bigger ring at the center, formula B is equal to mu naught upon 4 pi, okay, I into 2 pi capital R square plus R square plus x square to the power 3 by 2. This is the formula for ring, magnetic field due to ring at any point on the axis at distance x. As we are interested in finding the field at the center, then x has to be 0. So for x is equal to 0, we are getting B is equal to mu naught upon 4 pi I into 2 pi R square divided by R square plus 0 to the power 3 by 2. This R cube will get cancelled out with R square in numerator. So mu naught upon 4 pi I into 2 pi divided by R cube, only R will be left. So this is the formula for the magnetic field at the center. And to get the flux as the size of this ring is very small, I can assume that whatever we are getting on axis almost same is the magnetic field at every point on this ring. For this condition we are writing, okay. So, I hope the situation is clear. Now, phi is equal to what we can write, mu naught upon 4 pi. Let us first write the formula. So, as the area vector of this one and the magnetic field both in same direction, area vector for this ring will be like this, and you can see the magnetic field is coming in the same direction. Dot product mod B mod A cos 0. Okay. So, mod B is area of this one pi A square, and this is the flux associated with the ring. So, this is the procedure we need to follow. If this become little bigger, if this is a little bigger, the problem is we cannot calculate the magnetic field at any other point on the plane, okay, because it will be mathematically complicated. So, at your level that much complication in mathematics you cannot handle, okay. So, the points will be given or the situation will be given in such a way so that you can easily integrate the function, right. So, this is clear. So, previous one, these two are mutually perpendicular, and in this case these two are parallel. Then how to find out flux? I hope this is clear. Similarly, if I give you another situation, let us take one more situation. This bigger one is something like solenoid. Okay. So, inside solenoid we have one ring. So, inside solenoid we have got one ring. Ring is something like this. And it carries current I. This is the direction of current. If it carries current I and the number of turn per unit length is n, then we know the magnetic field formula. B is equal to mu naught Ni. Okay, field comes uniform inside. So, field pattern will be this way. I will draw another diagram. So, this is the way we have field lines inside, and now what I am saying is, if I keep one loop inside, how much is the flux associated? So, let the axis of this one is along x direction. So, this is our x axis. Okay, so this is x axis this one is y axis, and I am keeping loop which is making some angle. With x axis, the angle made by this one is say 37 degree. Okay, I hope diagram is clear. This angle theta, okay, this is 37 degree. Radius of this bigger loop is r, and the radius of this one is say a. Okay, so radius here is a. Now question is, what is the flux passing? So you already know the magnetic field formula. You can derive that formula using Ampere's law also, right? So I can write A in vector form, that is pi a square in bracket cos 37 I cap cos 37 I cap plus sin 37 j cap. So let's simplify. Pi a square in bracket we are getting cos 37 4 by 5. So 4i, similarly sin 37 3 by 5 3j, and 5 I am taking out. So this is vector A. What about magnetic field? Magnetic field inside B is mu naught Ni. Okay, so mu naught Ni, and the direction of that is magnetic field. You can see magnetic field lines are along I cap. So mu naught Ni I cap. Flux, as the magnetic field inside the solenoid at every point is same, right? So what we can do? We can write magnetic field into area, right? B dot A area, A vector. So area vector, let's write capital A here. So mu naught Ni, this is I cap dot in bracket pi a square divided by 5 4i plus 3j. If you do dot product, then it is mu naught Ni I dot I 1, I dot j 0. So next term will become 0. So directly I can write pi a square by 5 into 4. Okay, so this is the flux associated with the coil placed inside solenoid. So more or less every type of problem we have done on flux. So I hope flux part is clear. We already discussed the flux part there in electrostat. So still you are finding it difficult to understand. So I have discussed a number of problems there. You can go through those problems. Okay, so concept is same, approach is same. Only thing we require is the direction of magnetic field and the direction of area vector. Once we have these two, we can easily find out flux. Variable, magnetic field is variable, then you need to integrate. If it is constant, then you can directly multiply with the area vector and you can get the answer. Now, so this part is clear. Let's see. So I'll just introduce Faraday law. Okay, so we just discussed flux. Now what happens when this flux changes with time? You are seeing that in these cases flux magnetic field is varying with distance. Okay, B is a function of r. So if B is a function of r, the flux passing through this one for every elemental area will be different, but it is not varying with time. Okay, but if it start varying with time, for example in this case, if I start varying this current, this current density, it is a function of distance, and this also become the function of time. For example, if I see previous one here, this current is a function of time. For example, if I say I is 2 t square, earlier when we discussed the problem, we assume this to be constant, right? Now I am saying this current varies with time. So what happens when this current varies with time? As there is a flux associated with the coil due to the presence of current, if I change current with time, the flux associated with this one will be changing with time. And what Faraday observed was, when flux associated with closed loop changes with time, it produces induced EMF in the coil, right. So the electron which are there inside this wire, they start experiencing force, and as they start experiencing force, they start moving. When they start moving, there exists a current. You can see there is no source of current, but when you change this current, here current is getting induced. So this is called induced current, right. We have seen the induction of charge. So if we have a metallic sphere and I bring one positive charge, then there will be redistribution of charge, right. Negative charge start appearing here, their concentration will be more, and positive charge will be somewhere here, their concentration will be more here, right. So charge was getting induced, but in this situation current is getting induced. So current is getting induced due to the induced EMF in the coil. There is no actual source in the coil, but even then there is a current in the coil. How that current varies, how to calculate that we will see in the Faraday law, but for time being I am saying today we have just calculated flux, okay, and in all the cases I consider flux to be constant, but when flux start changing with time, okay, when flux start changing with time, then what happens? So according to Faraday's first law, when flux start changing, there will be EMF induced in the coil. This we will discuss in the next class, okay. So today we just completed flux. Next class we will be talking about the effect of changing flux, right. So I hope you enjoyed today's class. Thanks very much for watching, and do download the assignment what I gave on the flux and start solving. If you have any doubt, you can post your doubt and I will try to answer it, right. So very important chapter, you have to pay more attention to this one because this is having more weightage. So frequently question come from this particular topic, right. Okay, thanks.